you can read those. So the last section is nonlinear PDE, which is again a big subject, huge subject, because nonlinearity, again, you can have many different forms of nonlinearity, and like linear is just one form. Right? Nonlinearity is you can be nonlinear in many different ways. And then so your textbook has an example, which is an interesting one, and also is an example of a huge subject. Also, is about Soliton. You can have a whole course on Soliton and still not cover everything. So, but this is an interesting example. It's called the KdV example. I mean, you have the full pronunciation, but most people call it KdV equation. But the form of the equations is like this. So this 9.24 is the form of the KdV equation. Positive psi, positive t, psi, positive psi, positive x plus the cubic derivative, third order derivative. Equals to 0. Okay. So the first two terms is like what we did in the first order ODE, and except that the coefficient is not a constant. Instead, this is actually a function of psi. It's just basically just a linear function, but that makes the equation nonlinear, obviously. And so, but you can say that in some approximate sense, this represents just like what we did with a constant coefficient. Remember, if we just keep these two terms with a constant coefficient, we have a equation. We can just write down the equation using the transformation variable and characteristic, and then write down the solution right away. And it looks like a propagating solution, basically any function of a form that if this is like c, right? This is the speed of the propagation, x minus ct, any function x minus ct is a solution, right? But now that is actually the variable is psi. So it takes this psi takes looks like it takes the role of the speed, and so this Soliton will also have propagating solution, but then the propagation speed actually vary with the height or the how large psi is. So it's amplitude dependent propagation velocity. That is one property of Soliton. So the Soliton speed is not exactly the same as the higher, larger magnitude, it propagates faster, right? And that sometimes you can observe. This is a model for like so-called shallow water wave. So the wave, this is with shallow means the wave, the height of the say you have some kind of body of water, and then you have some kind of floor, right? And then this length is the depth of the water. The depth of the water is much larger than the wave amplitude is called. So so you can describe this kind of wave, right? And now the one property that the amplitude dependence solution is that you have an initial perturbation, then you can regard that as this is psi, right? And larger psi will propagate faster than smaller psi. So this it tends to propagate and to deform, right? And the highest one will move faster, so it can roll over. So this describes some kind of a ocean wave that people observe. So you have a wave-like structure. So for arbitrary initial condition of arbitrary perturbation, it tend to have something like that. The top of the wave will try to roll over. So that kind of this is some kind of model for that. But then this, you have this cubic term, and this if you talk about wave that make it you do Fourier transform of that Fourier transform in space, that would give you a KQ, and you do a Fourier transform in time, this would be omega. So this the what we call the dispersion relation omega is depends on k. It's not linearly depends on k. When the relationship of omega depends on k is called the dispersion relation. And if this is not linear, it's omega not linear, it depends on k, then that we call that the dispersive wave. So it means the wave, the group velocity of the wave will tend to depends on k. So the group velocity is d omega dk. Right? I don't know whether did you talk about that? Not maybe in E&M, right? If omega is not depends on k, this group velocity is a function of k, right? It means it depends on the composition of the wave. Some k will move faster, some k will move slower, right? And in general initial condition, then we will try to, and when it propagates, we will broaden. The whole thing move in VG, but then the composition of different k change differently. So there are two effects. One is but this effect, you try to roll over, the wave try to roll over. And the other is the wave try to broaden. Then finally, there's some kind of special solution that these two effects kind of cancel each other. So there's some kind of special initial conditions, the wave of this kind of the certain shape of the initial profile of the function psi. Then it will propagate at a certain speed, and then will keep the same shape. It doesn't broaden, and then doesn't change the shape. It's just propagate as a pulse. And that's one property of Soliton. It's not the only, and maybe not the definite property. There are other properties like speed dependence. Propagation speed is still right. Like if you have an initial pulse like that, and plus another initial pulse. I mean, usually you cannot add two solutions together, but for the case of Soliton, because it fall off to zero quite fast, we see that the solution right away. But after it fall off to zero, then you can add another solution like that. But that's still a solution, a very good approximation, because both fall off already, and so both propagate. But then, because this one has a larger amplitude, this one will move faster than this one. So we'll try to pass it over later in time. So the whole thing, this one will move to here, but then this one already passed it. This one move faster than this one. Just now overtake this one, the slow one. And one major property of Soliton is that after it passes it, the shape basically is unchanged. The position shift a little bit, the so-called the phase shift a little bit. There's other than the phase shift, the shape of the two pulses still the same, remain the same. And that's very interesting so-called. That's a more definite property of solitons. So in this example, we're trying to find form of this kind of a soliton solution, this kind of special solution, right? And so we'll try to solve it, and by simply assuming that it will propagate at a certain speed. So the form we assume is psi is psi as what the textbook use x minus c c. Using this variable to c, which is defined as x minus ct. This c is to be determined or to be specified as your parameter of your problem. Right? But we assume you have a certain parameter, and the solution propagate in this kind of form. And this obviously is I mean, the arbitrary function, but this arbitrary function just move in time and propagate in the x direction using the speed c. Okay, and then we'll just plug that form into here, and then find a differential equation of the c that becomes ODE. Okay, and that's what we'll do, and we propagate it in this one. So just write partial psi, partial t will be partial psi, partial c, and then the argument partial c, partial t, right? Partial c, partial t is minus c, right? And so that's the first one. And then we also need this derivative, and that becomes easier because partial psi, partial x is simply partial psi, partial c, and then partial c, partial x is just 1. So basically the same, right? And then the third derivative is obviously you can keep doing that, and just q, partial xq is just psi, partial c, q, right? And then we just put everything back to here, and what we have is also and I mean, because this is as a function, we can actually change all these partial derivative to ordinary derivatives. It doesn't matter. This we don't need to do partial derivative because this just depends on a single variable. Okay, so what we have is this is minus c times d psi dk c. This is d psi dk c. So you can combine these two. Psi minus c d psi c. And then the third one is dq psi. That equals to 0. Right, and then the first term, you can combine this product to a total derivative. And this is already a total derivative. So the next one you can write is dd to c. So this term becomes psi squared over 2, right? You take a derivative of that, you could put a factor of 2, cancel the 2 in the denominator, and become psi d psi dk c. Right? You see that? Yeah, right. And the second term is just minus c. And then this, the last term is just you pull one derivative out, d squared psi dk c squared. That equals to 0. Right. And c side. I forgot c times dc with c side, we can pull out a constant c. side. You can see, right? And so because it's total derivative, that's so the whole thing becomes just a constant. And now we use our boundary condition. We require this solution to be 0 at infinity. So they initially set it to center at a certain origin. So, but as the c goes to plus or minus infinity, so you require psi equals to plus or minus infinity equals to 0. So that's the boundary condition for this kind of solution, right? And so the whole thing equals to a constant, but then psi need to go to 0 at infinity. When psi goes to 0 infinity fast enough, the derivative will also goes to 0 because the whole thing goes to 0, right? And obviously the derivative and higher derivative will all goes to 0. The psi will go to 0, psi goes to 0. Second order derivative of psi also goes to 0. So the whole thing goes to 0 at infinity. So you can just immediately write down your, now the differential equation becomes d squared psi equals c squared. You can write it like in the form of c psi minus psi squared over 2. Right? Just move this term to the other side. Right? So I mean, this is essentially 9.25, except that I write, this is 9.26. Just move the other term to the other side, to the right-hand side. And this form you know how to solve, right? How to solve? We talk about that in class. What do I call this kind of form of solution? This kind of differential equation. You asked me about one homework question, right? The right-hand side is e to using this kind of notation becomes e to the psi. But the homework problem is e squared y dx squared equals e to the y, right? Remember that? That example homework. you can solve it exactly the same way, right? And what I call it is like a potential problem. Right? This is we encounter in physics quite often. The second derivative, like acceleration, treating c as your time derivative. This is acceleration, and so the right-hand side becomes your force, right? And so it's like solving the second order. The force would depends on the location of your so this becomes a position, psi becomes a position. The force depends on the location, and it may be a general function. So this is coming from a potential, something like a potential give you a force, and then you solve the Newton's second law, right? So that kind of what we call the potential problem. And what do we do with the potential problem? To reduce the order, what do we do? Simple harmonic motion. It's not quite, because it's not simple harmonic, right? Simple harmonic motion is this is you don't have the nonlinear, right? It's not simple. It's more complicated than that. Remember that you have a potential problem. You reduce the order by finding a conservation energy, right? That's your general physics, right? You do TA for general physics, right? Some of you did, so you solve Newton's second law. Easier way to solve Newton's second law is convert that to conservation energy, right? Remember? So that's the same thing. To get to a conservation energy, you just multiply by this acceleration, right? Multiply by the velocity. D psi, the c, d squared psi. So that's the left-hand side, and that combined to 1/2 of dd c. beside you can see. Right. This one you work out the derivative. Pull out a factor of 2, cancel with this one. You have d sine d can see times the second derivative, d square sine d can see square. So that's this one, right? So that's the left-hand side. The right-hand side you multiply by the same d sine d can see c sine minus sine square over t. Right. And also you can put it like total derivative. And again, this one becomes doing the same trick. This is sine square. And but this one, this is already have a sine square, so that will give you a sine cube. And you need to figure out the coefficient. Sine cube will pull out a 3, so you need a 3 in the denominator minus sine cube over 6. Right? Right. You take a derivative of that. That pull a factor of 3, cancel that becomes a 1/2, right? Then your sine square and d sine d can see, right? That make it a total derivative. So the left hand side is a total derivative, right hand side is total derivative. Again, you combine the two. The total is a constant, right? Then again, you use the boundary condition, and psi goes to 0, and also the derivative goes to 0. So that this sine d can see also goes to 0 at infinity. So the whole thing equals to a constant. So the reduce all the differential equation become d sine d c square equals to, you can multiply factor of 2 to the other side. The c sine square minus sine cube over 3. I mean, if you like, you can take a square root of the right hand side and get this side you can see, right? But then obviously you have you need to be careful. If the right hand side is negative, then you need to avoid that, because all these we are trying to solve a real solution. It becomes negative. Take the square root, become compact. Okay, so you need to consider the situation. Okay, so that becomes the first order differential equation, and you know how to solve it, right? Because after you take the square root, assuming this is positive, and then that becomes separable, and then you can integrate that. Although that the integration is straightforward, it might take a little bit of work, but the good thing is your textbook already give you the solution. Then you can just use a trick that we check your solution. After you get a solution, you want to check it anyway. So if you plug in and check it, if it satisfies the equation, then it's a solution, right? So why don't we just do that? Just check the solution in your textbook, right? Let's just find some space to still maybe to erase something. Let's erase picture. So the solution given in your textbook is, right, x minus ct is just c is equals to 3c divided by cos square and half square of c divided by c divided by 1/2 divided by 2, and x minus ct is c. Right. That's the solution given in your textbook. So all you need to do is just now for this one, you can just check the final equation. I mean, assuming you divide it correctly, you can actually try propagating substituting back to wherever we start this equation. it doesn't matter. You see that it should be the same. So let's just do it this way. You just need to do one derivative. And 1 over cos actually what we call sinh, SC. But doesn't matter. We could just do it anyway. D sine. So following the rules of minus, this is square, so minus square in the denominator, so minus 2 and times 3 becomes 6, minus 6c. Oh, shoot. C, and then take the derivative of the cos function. C function. Right, and then take the derivative of the argument of the sinh function, and that gives you square of c over 2. Right. Is that okay? Is my derivative? This the one. Okay. So that's the design you can see. And now we need the square of that. We need the square of that. Square equals to cancel with that. 3, so 3 squared is 9. And then C, this gives you C, the C squared C cubed. C cubed. And whatever that argument, cos 6 power. Okay, that's the a square, yeah. So that's the left-hand side, and the right-hand side is C psi squared plus I cubed. I mean, we can pull our psi square out first. Psi square is 9c squared cos 4th power. Right, and C minus psi over 3 becomes, right? Psi over 3. Psi over 3 cancel with this with the 3. This becomes C and cos 4 by psi squared cos 4. Right, that's the no, it's not square. This one is not square. This is just we pull out psi square, pulls out psi square, right? This becomes C minus psi over 3, just psi over 3. Okay, so need to be a little careful. So that's the right-hand side. Now we simplify that. So C and C, common factor get out, becomes 9c cubed. The common denominator, cos square and 4 cos 6. And then the numerator is cos square minus 1. And what is cos square minus 1? Sinh, right? Yeah, that's sinh. It's 9c cubed. Sinh square. You know that, right? Most of you know that. Cos square minus sinh square is 1. Right? Just like for sine and cosine, sine square plus cosine square equals 1 for hyperbolic function. Yeah, this you have a minus sign. Cos is greater than sinh, right? You know that, right? Right. The cos square minus sinh square is equals to 1. The cos square minus 1 is sin square. 6. That's the right-hand side. What's the left-hand side? Left-hand side is this one, right? Right-hand side, this one, so this two are the same. Okay, so we check that. So this is your solution of this one, which is after you do all this, reduce order and set the boundary condition, which is this equation, and that's coming from this equation with this substitution. So, all right, so that's the solution. We check that. A little bit of work, even just check it. But the integration is actually not difficult to integrate the separable solution. You just maybe look up the math handbook and found the integral. Okay, but once we have that, we can look at the property of that. So you know that this c is in the argument. So this is the speed of the propagation of this function, the solution, right? So obviously psi is proportional to c. So the amplitude of the solution is proportional. C is proportional to the propagation speed. So that's what we started to say. This kind of solution, the propagation speed depends on the amplitude. The higher the amplitude, the faster it propagates. Right. So that is one. And then also the c going into the argument of your function. So with the fixed function cos square in the denominator, whatever function, so that is like a wave number, right? Of that, because you multiply by the c basically is spatially depends on x. So this is like your wave number or inverse wavelength, right? Or the width of your solution. So you have some space here. So you plot this as a function of c, right? Then the height will depends on c. The height will proportional to c, and the width of this part will be proportional to inverse of square of c, right? So this basically is like the wavelength. Right? Inverse of the wavelength with the wave number. So that's how wide this route. So the larger the amplitude, the narrower is the pulse. So that's kind of property of your soliton. And then for large, you see in both positive and negative direction, it goes to zero very fast because you know the cos is proportional exponential function for large argument, but it's in the denominator, so exponentially small, actually exponential square. So also e to the whatever this function in absolute value in the denominator for both positive and negative infinity, so it falls off very quickly. Right. Okay, so that's one sort of solution. Depends on one c. If you have another c value, c becomes a parameter. You can choose another value for c. So you can have a smaller amplitude, but then for the same solution, it becomes wider. You can have a solution like that and propagate slower. Right? Those are the property of these special kinds of soliton solution. It's okay. So, but obviously the original solution can have more solution than just soliton. So soliton is a special kind of solution, but depends on your initial condition. You can have arbitrary shape as your initial condition. Okay. Yeah. All right. So that's one example. It's a special example. Not all nonlinear equation can be solved that easily. I mean, kind of easily. At least you can solve it with analytic function. Many nonlinear solutions will have no analytic solution. That's just the way it is. But it's still an interesting one because it's had some interesting property, and it's, I mean, it has some general idea about soliton, also just an illustration of, I mean, there are many other soliton equations, but this is one example, illustrate some property of soliton in general. Okay, so that's the end of 9.3. Any question of the whole section, or this in particular this KdV equation? All right.